Hi, we're going to calculate the standard molar enthalpy of formation. Now, the symbol for that is the delta H. You have a superscript of a 0 and a subscript of F. Now, the superscript 0 represents standard temperature and pressure. Okay, another symbol that's often used is the delta H, superscript 0, and then the subscript would be an RXN for reaction. Now, the definition for standard molar enthalpy of formation is the energy released or required when 1 mole of a substance is formed directly from the elements in their standard states. Okay? Now, mathematically, we can use the following equation. So here we have the enthalpy of reaction. So instead of using the subscript F, we have reaction. It's going to equal, now that's the Greek letter sigma if you haven't seen it. That represents the sum of the heats of formation of the products. Now notice you have the letter N there, which represents the moles. You have to multiply the heats of formation of the products by the number of moles that are in a balanced equation. Okay, again, enthalpy is an extensive property, so if you increase the amount of products you have, it's going to require more energy. Okay, then we're going to subtract the sum of the enthalpy of formation of the reactants. Now, a couple things to remember before we get started. The first one is the enthalpy of formation for elements in the standard state is 0 kilojoules per mole. Okay, this is because an element is already in its stable state. Now don't forget the 7 diatomic elements. These guys are in their stable state, so the enthalpy of formation for them is 0. We have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Also, take a look at any data table that you have or booklet. Okay, here on about page 4 or 5 of our data booklet, you should be able to find the standard molar enthalpies of formation. And notice it's at 298.15 kelvins. That's standard temperature. Okay, in this column on the top, the left-hand side, it gives you the name. In the middle, it'll give you the formula. So if you forget how to write the formula of some of your elements, you can look them up. And then you have the enthalpy of formation. The units on that enthalpy of formation is kilojoules per mole. Okay, let's get started. We're going to do an example where we're going to calculate the enthalpy of formation for glucose. Now this is a photosynthesis reaction. So we have 6 moles of carbon dioxide, 6 moles of H2O liquid, so it's not vapor, it's liquid. This will produce 1 mole of glucose and 6 moles of oxygen gas. Before we get started, I just want to make sure that my equation is balanced. That's the first thing that you should always do. Okay, now you can balance this using inspection, but I often like to write down the little initials LS for left side. It should equal RS for the right side. Okay, so the first element I'm going to check on is my carbon. On the left side here, I see I have 6 carbon atoms. On the right hand side, I also have 6 carbon atoms. So my left side and my right side in carbons is balanced. Okay, then I'm going to look at my oxygen. In the first species there, I have 6 times 2, so that's 12 oxygen atoms. Second species on the reactant side, it's 6 oxygens, so that gives me 18 oxygens on the left. When I move to the right, my first species gives me 6 oxygens, and the second species, 6 times 2 gives me 12, so that's 18. So again, my oxygens are balanced, left side equals right side. And then the last atom to check for is hydrogen. 6 times 2 is 12 on the left. On the right, well, there's just the subscript 12, so we have 12 hydrogens on the left and 12 on the right, so it's balanced. Okay, now we can move on. So there's my balanced equation, and I've written the standard enthalpy of formation equation right below it so I can keep track. Now I've got to sum up the heats of formation of my products, and then I'll subtract the sum of the heats of formation of my reactants. So when I look at my first product, I notice that I only have 1 mole of glucose. So I'm going to have 1 times the heat of formation for glucose. Okay, then I have 6 moles of oxygen, so that will be 6 times the heats of formation for oxygen. Okay, then I'm going to subtract, and now I'll sum up the heats of formation for my reactants. Okay, looking at my reactants, I got 6 moles of carbon dioxide, so that will be 6 times the heats of formation for carbon dioxide. And now 6 moles of H2O liquid, so 6 moles of heats of formation for H2O liquid. Okay, now watch the states. I didn't write them down here, but they are in the balanced equation, so keep a close eye on those states. Okay, now I'm going to look at my data table. So again, there's the title of the data table. You have your name, formula, and your heats of formation. Okay, the first species I'll look for is glucose. So there's the name glucose. Check the formula. Yep, it's C6H12O6 solid. States are good. Heats of formation is negative 1,273.3. Okay, next species is oxygen. Now, when I look in my data table, I can't find oxygen. That's because it's in its elemental state. So the heats of formation for oxygen is 0. It's not in the data table. Next species is carbon dioxide gas. So I find my carbon dioxide, the formula is CO2 gas, so the state's good. Heats of formation, negative 393.5. Okay, and finally, my last reactant is H2O, and it's liquid. So I look for water, and I want the liquid form. So there's water, liquid form, H2OL, that's good, and the heats of formation there is negative 285.8. Okay, now I'm just ready to put those heats of formation into my equation, and then it's a matter of plugging those values into my calculator. So on the next slide, there's my heats of formation equation with all the moles and etc. written down, and then their values. Okay, so I'm going to replace all of the values into the equation. So I've got 1 mole times negative 1,273.3 kilojoules per mole. Now I put the units in the very first species here so that you can see that the moles will cancel out. Okay, and all you'll be left with is kilojoules, which is the units for our enthalpy. Okay, now plus I've got 1 mole of heats of formation of oxygen gas. Again, oxygen is 0 kilojoules per mole, so but I'll put it in there, 1 times 0. You can omit this if you like. Now minus 6 times the heats of formation for carbon dioxide, so 6 times negative 393.5. Now plus 6 times the heats of formation for H2O liquid, so 6 times negative 285.8. Okay, now I'm just going to calculate what the heats of formations for that first bracket, my products, is, and I get negative 1,273.3 kilojoules. Okay, remember we have to subtract the heats of formation of the reactants, and when I calculate those values, I get negative 4,075.8 kilojoules. Okay, when we do the final calculations, you want to watch out because you have 2 negatives in a row, and 2 negatives in a row become a positive value. So when we do those calculations, we get positive 2,802.5 kilojoules. Okay, so the enthalpy of formation for 1 mole of glucose is 2,802.5 kilojoules. Now, this is an endothermic reaction.